Work done in engine cycles. A heat engine uses a heat source to do work, then passes any unused heat to the surroundings. The first law of thermodynamics applies to heat engines. That is, delta U is equal to Q plus W, where U is the internal energy, which is directly proportional to the temperature of the gas. So if the temperature of the gas is constant, so is the internal energy. Q is the energy supplied to the gas by heating, i.e. this is from a higher temperature source. And W is the work done on the gas. This is where no higher temperature is needed. Note that heat energy supplied by the gas will be minus Q, and work done on the surroundings by the gas will be minus W. When a gas is being rapidly compressed or expanded, there will be negligible heat energy entering or leaving the system, so the Q term will be equal to 0. In this case we can have delta U is equal to W, meaning that the work done on the gas, W, is causing an increase in the internal energy of the gas, delta U, and therefore causing a temperature rise of the gas. Alternatively, we could have minus delta U is equal to minus W. This means that the internal energy, and therefore the temperature of the gas, is falling, as it does work on its surroundings. Changes where no heating occurs and the Q term is 0 are called adiabatic changes. A gas can undergo changes with no temperature change. These are called isothermal changes. Iso meaning same, and thermal relating to temperature. Here, delta U, the change in internal energy, is 0. So we can have Q is equal to minus W, meaning the heat energy supplied to the gas allows it to do work on its surroundings. Or we can have minus Q is equal to W, where work is done on the gas, but it transfers the energy gained to the surroundings through heating. These changes can be represented on a pressure against volume graph. It would have a shape something like this, if the temperature were constant. Considering the area underneath the pressure against volume graph, it will be found by multiplying a pressure, the y-axis, by a volume, the x-axis. So the area under the pressure against volume line gives the work done, which is found from pressure times change in volume. I'm now going to consider a very simple heat engine before looking at the behaviour of the gas graphically. Here we have a piston inside a cylinder, and in this part of the cycle the piston is moving in, compressing the gas. There will be effectively no heat entering or leaving the system, so this is adiabatic compression. If we now apply a heat source to the compressed gas, it will tend to increase the internal energy of the gas. But if the piston moves out at the same time, this will tend to cause a drop in the internal energy of the gas. If the two are balanced, we will have isothermal expansion, no change in the internal energy of the gas. Removing the heat source while the piston continues to move out will cause the gas to cool. This is adiabatic expansion. We now apply a cold sink to the trapped gas, which would tend to lower the internal energy, but if the piston also moves in, this would tend to raise the internal energy. Again, if the two are balanced, we have isothermal compression. Overall, no change in the internal energy of the gas. Removing the cold sink while the piston still moves in, we now have adiabatic compression. Now we'll look at those stages graphically. First, adiabatic compression. Adiabatic compression of the gas will cause the internal energy, and so the temperature of the gas, to rise. Both these factors lead to a pressure rise in the gas. This will happen, for instance, when the piston compresses a sealed gas with no cold sink available. This would give a line something like this. Here, quite a small drop in volume is causing a large rise in pressure. Next, we'll look at isothermal expansion. Here we have no temperature change, so the pressure drop will be less. This happens when the piston is pushed out, as the gas absorbs heat energy from the hot source. This would give a line something like this. Now we have a large volume increase for quite a small pressure drop. Next, adiabatic expansion of the gas will cause the internal energy and so the temperature of the gas to fall. The gas no longer gains energy from the heat source. Both these factors lead to a fall in pressure, giving a line something like this. We now have a large drop in pressure for quite a small increase in volume. Now, isothermal compression. Here we have no temperature change, so the pressure rise will be less. The gas loses heat energy to the cold sink as it is compressed, giving a line something like this. A large drop in volume gives a relatively small pressure rise due to this loss of heat energy to the cold sink. Putting all these four stages together, we get a cycle. Starting with adiabatic compression, where the change in internal energy is equal to the work done on the gas. We compress the gas with no access to a cold sink. Next, we have isothermal expansion. Here, the heat energy supplied to the gas is equal to the work done by the gas on its surroundings. As the gas expands, we provide energy to it from the heat source. Next, we have adiabatic expansion. Here, the drop in internal energy of the gas is equal to the work it does on the surroundings. It is now expanding, but with no hot source available. And finally, we have isothermal compression. Here, the heat energy supplied by the gas is equal to the work done on the gas. We're compressing the gas, but the cold sink is taking away the heat energy produced by the work being done on the gas. This is known as the Carnot cycle and applies to an ideal gas taking energy from a hot source at absolute temperature TH, which would be represented by this line, and losing heat energy to a cold sink at absolute temperature Tc, represented by this line. The area enclosed by the Carnot cycle represents the work done by the gas on its surroundings. The internal combustion engine follows a slightly different cycle. Starting with induction, as air is drawn into the cylinder, we have it open to the atmosphere, and so there is no change in pressure as the volume of the cylinder increases. Next, we compress the gas with no heat source, so this is adiabatic compression. When the gas is compressed, we then ignite the gas using the spark plug, and there will be no change in volume, but a massive rise in pressure, like this, during the combustion phase. As the combustion stops, the piston will move out, causing adiabatic expansion of the gas. Heat energy gained during this phase will now be transferred to the surroundings. And finally, the exhaust valve is opened, and we go through the exhaust phase as the piston expels the gas from the cylinder. The cylinder is open to the atmosphere, so there is again no change in pressure during this phase. This is known as the Otto cycle.